Today we're going to learn about motional EMF. Let's introduce this topic by first exploring the following example. A conductor is moving through a uniform magnetic field B at speed v. As a result, the positive and negative charges in the conductor separate, thereby inducing an electric field. What must be the induced electric field after the charges reach equilibrium? And what is the induced potential difference between the charges? Let's start off by sketching our conductor. And initially, let's suppose our conductor has positive and negative charges within it. So we'll indicate that with this representing a positive charge and this one representing a negative charge. Now our conductor is moving to the right with the speed of v. Currently inside this conductor, the electric field is 0. Now you can look at that being 0 because these positive and negative charges negate each other's electric field at every point in space. Now let's look at what happens when we have this conductor moving in a uniform magnetic field. We'll indicate this uniform magnetic field by drawing a series of X's representing that the magnetic field is pointing straight away from us directly into the screen. So here the electric field is in front of the conductor, it's behind the conductor, and it's passing through the conductor. Now let's look at what happens when this conductor is moving through the magnetic field. You know that a point charge will experience a magnetic force equal to the product of the charge's charge and the cross product between its velocity and an external magnetic field. Now you know from the right-hand rule that the direction of the magnetic force will be perpendicular to both the velocity and the magnetic field. Where remember, we could determine the direction of the magnetic force by putting our fingers in the direction of the first vector, which is the velocity, face our palm in the direction of the second vector, which is the magnetic field, and the direction our thumb points after we stick it out is the direction of the magnetic force. Now this would be the direction of the magnetic force for a positive particle. So let's look at the right-hand rule for this positive charge. So this positive charge is moving to the right, being in the conductor, and notice our right hand is pointing to the right. Now we're looking down on top of our right hand, so our palm is facing away from us in the direction of the magnetic field, and notice that the thumb of our right hand is pointing straight up. So this is the direction of the magnetic force for the positive particle. So let's indicate that in our picture. The magnetic force on that positive charge is going up. Now negative charges behave exactly opposite to positive charges. So the magnetic force on the negative charge is going straight down. Due to the magnetic forces on the positive and the negative charges, those two charges will begin to move to opposite sides of the conductor. The positive charges will move to the top edge of the conductor, while the negative charges will move to the bottom edge of the conductor. This process will happen for all of the positive and negative charges that are in this conductor. The positive charges will accumulate on the top edge, while the negative charges will accumulate on the bottom edge. And at some point, these charges will reach equilibrium. And the reason why that is because when these charges separate, there will then be an electric field. So the electric field will no longer be 0 in this conductor. The charge separation creates or induces the electric field, or rather, the motion of this conductor in this magnetic field causes an electric field to be induced because the magnetic forces on the charges separate the charges. And these charges will then create an electric field between them, between the positive and negative charges. And the electric field is not zero. It's going to be a particular value. And that's going to be our goal, is to determine the electric field. Now, if we look at one of these charges, let's take a look at this positive charge. That positive charge will reach an equilibrium between the magnetic field and the electric field acting on it. Now remember, the magnetic force is equal to the product of the charge and the cross product between the charge's velocity and the magnetic field through which it's moving through, while the electric force is equal to the product of the charge and the electric field. And after a period of time, these two will be in balance. This positive charge will be in equilibrium. And our task is to determine the electric field that was induced by the motion of this positive charge within this magnetic field. And so we could do that by looking at the net force on this positive charge. So the net force on this positive charge is just the sum of all of the forces acting on this charge. And for this problem, we only have the magnetic force and the force due to the electric field that is induced between the positive and negative charges. And that sum is equal to 0 because our charges are in equilibrium. So this net force is given by the positive charge times the cross product between its velocity and the magnetic field minus the charge times the electric field, which is going downward, and this is equal to 0. Now, the same charge appears in each term, so we could cancel that out. And we end up with the electric field being equal to the cross product of the charge's velocity and the magnetic field. And if we want to know the magnitude of the electric field, the magnitude of the electric field is just equal to the magnitude of the product of the particle's velocity and the magnetic field times the sine of the angle between the particle's velocity and the magnetic field. Well, since the particle is moving at a right angle perpendicular to the magnetic field, the angle between the two is 90 degrees. The sine of 90 degrees is 1. So we have that the magnitude of the electric field established in this conductor is equal to the product of the conductor's velocity and the magnetic field. So notice this result is independent of the number of charges we have that are free to move in the conductor. This result depends on the motion of the conductor in the magnetic field. So let's look at the sequence of events that led us to this result. So we see that we've induced an electric field. We started off by looking at the charge carriers. If we just follow the journey of the positive charge carriers, we know that it experiences a magnetic force whose magnitude is just the product of its charge, its speed, and the magnetic field. Due to the magnetic forces on the positive and negative charges, we saw that those charges separate, creating an electric field due to their separation. Now, the charge separation will continue until the downward electric force in this sketch balances the upward magnetic force, allowing the charge to reach equilibrium. So this sequence of events led us to the conclusion that the magnetic force on the charge carriers in a moving conductor creates or induces an electric field inside the conductor.